Let's take a deep breath. Smell of searing steak, freshly baked bread, or freshly roasted coffee beans isn't just appetizing. It's the smell of a magnificent, chaotic chemical symphony between carbohydrates such as glucose and fructose and amino acids such as lysine or arginine. And the best part, you don't need $1 million scientific laboratory filled with glassware that's really expensive in order to run it. All you need is your kitchen and a little bit of heat. But the very same chemical reaction that makes culinary dishes taste delicious is silently happening inside our bodies at 37 degrees Celsius, or 98.6 degrees Fahrenheit. And so this acts as a slow cooking process that accelerates aging, tissue stiffening, and diabetic complications. That chemical reaction is called the Maillard reaction, the single most delicious reaction in the universe. And it also has very important biomedical implications depending on where it's run. So for a bit of history, the Maillard reaction was first discovered in 1912, about a little over 100 years ago, by French physician and chemist Louis-Camille Maillard. And its mechanism was finally worked out in 1953 by a chemist, John E. Hodge, working at the U.S. Department of Agriculture. And the Maillard reaction is responsible for many colors and flavors in foods, such as the browning of various meats when seared or grilled, the browning and the umami taste in fried onions and coffee roasting. It also contributes to the darkened crust of baked goods such as chocolate chip cookies, the golden brown color of French fries, and other crisp, and even the browning of malted barley and malt whiskey and beer. It should not be confused with caramelization. And so caramelization is just the sugars burning solo. There's no proteins added to it. Caramelization is simply the non-enzymatic breakdown of sugars. And this requires a fairly high heat, above 320 Fahrenheit or 165 Celsius. The Maillard reaction is a passionate team-up between the two distinct groups of molecules, reducing sugars and amino acids. And so let's just review our basic chemistry. A reducing sugar is a sugar that has an open open reactive carbonyl group. This is actually, it's not the carbonyl, this is the hemiacetal form. So glucose and fructose are reducing sugars, and of course we all know amino acids. There's 20 different amino acids. This is lysine over here because it's got a nitrogen in it. And so when you control the heat between 140 and 165 degrees Celsius, that's 280 to 330 degrees Fahrenheit, these molecules will crash into each other. They'll kind of come into contact, and then things get wildly complicated because there's a lot of different carbs and amino acids. Scientists still haven't really mapped out every single pathway this reaction can take, but we know the main stages. So let's trace the journey from raw to robust. Let's start with the molecule of glucose in its hemiacetal ring form. And this form is in equilibrium with the straight chain. So let's isomerize this to the straight chain aldose form, so we can actually see the aldehyde. And so the first phase of the Maillard reaction is all about condensation. The highly reactive carbonyl carbon on the sugar molecule gets targeted by the nucleophilic nitrogen of the amino acid. They bond and form an unstable compound called N-substituted glycosylamine. And a molecule of water is also formed during this process. But the molecule is not happy in its current state. It then undergoes a structural plot twist known as the Amadori rearrangement. So think of the Amadori rearrangement as the point of no return. The double bond between the nitrogen and the alpha carbon is shifted to the alpha and beta carbons, and this creates an unstable enolate. So the next step is a keto to enol tautomerization, and this creates a ketosamine. This is the launching pad for all the flavors that we love. At this stage, you can't see or smell anything different yet. The magic is still invisible. So phase 2 is where the reaction turns into a chemical fireworks display. The Amadori compounds dehydrate, fragment, and degrade, and they tear themselves apart and recombine into hundreds of new volatile flavor molecules. And depending on the specific amino acids and sugars that you started with, remember there's actually 20 amino acids and proteins, and glucose is certainly not the only carbohydrate. There's quite a few different carbs. So you get entirely different flavor profiles. Pyrazines and pyridines, these are going to give you earthy, roasty, and nutty notes that you might find in roasted coffee and cocoa. Furans and furanones, these are going to deliver the sweet caramel-like and burnt sugar aromas. And of course, pyrols and thiophenes, these offer meaty, savory, and toast-like smells. And so this is why a seared ribeye smells vastly different from a baking loaf of sourdough, even though the exact same underlying chemical reaction is driving both. So finally we reach the climax. That's going to be polymerization. And so the tiny volatile flavor molecules that we just talked about start linking up, and they bind together into a massive complex molecular chains called melanoidins. And melanoidins are large nitrogenous polymers that are responsible for the distinct brown color of the crust on your steak, the skin on your roasted chicken, the edge of your brownies. They don't just look pretty, they provide that deep savory complexity that's often referred to as umami. So now that you know the biochemistry, how can you use these to be a better cook? So there's 3 rules that you can use to maximize the Maillard reaction in your kitchen. So number 1, ditch the moisture. Water boils at 100 degrees Celsius, that's 212 Fahrenheit. And so that's way too low for the Maillard reaction to thrive. We need to crank up the heat. So pat your meats dry with a paper towel before cooking. If you still have all that water there, you're going to be kind of stuck in this system of, water kind of trying to boil, and you're just going to kind of boil your food. You're not going to run the Maillard reaction. Number 2, raise the pH. The reaction loves alkaline environments, so adding a tiny pinch of baking soda to onions while caramelizing them, or dipping pretzels in baking soda bath speeds up the browning process exponentially. And number 3, control the heat. You want to stay in the sweet spot of 140 to 150 degrees Celsius. If you go too low, your food boils in its own juices. You go too high, go above 180 degrees Celsius, 355 Fahrenheit, you leave the Maillard zone and enter the carcinogenic, bitter, and burnt carbon zone of caramelization. So remember, cooking is chemistry you can eat. Grab a pan, fire up the stove, and go run some biochemistry reactions on experiments on here. But before you go, let's also consider the very same reaction under different conditions is also implicated in your health, especially in diabetes, as well as inflammation. So how does all this stuff work? Let's remember that in chemistry there's three ways of speeding up a chemical reaction. First, of course, is increase the temperature. We've already kind of talked about that. This physically increases the molecular motion and enables the substrates of the reactants to physically bump into each other more often. Second is to add a catalyst, and that's a chemical or an enzyme that speeds up the reaction without becoming part of the product or products. And third is to increase the concentration of the reactants. More of something generally increases the likelihood that those ingredients will come into contact and actually react. You're just increasing the likelihood, right? So this is how the Maillard reaction, which is run at higher temperatures, can run silently, albeit more slowly, at lower temperatures, like 37 degrees Celsius or 98.6 degrees Fahrenheit. And that's human body temperature. So in vivo, this non-enzymatic reaction between reducing sugars and proteins is referred to as glycation. And under chronic hyperglycemic conditions, that's high blood sugar, that's like diabetes, the reaction accelerates dramatically, and this serves as a primary driver of diabetic complications. When circulating glucose levels remain persistently high, the Maillard reaction progresses through three distinct phases inside the bloodstream and tissues. Number one is the early stage, that's your Schiff base formation. So the carbonyl group of the glucose molecule reacts reversibly with an unprotonated primary amino group, typically the epsilon amino group of lysine residues, or the N-terminus of a protein, and this will form the unstable molecule, the Schiff base, rather quickly, within hours. Secondly, the intermediate stage of the Amadori rearrangement. Over several days, the unstable Schiff base will undergo a spontaneous chemical reaction or rearrangement to form a more stable, irreversible ketamine structure, and that's your Amadori product. And of course, number three is the late stage, and we call this advanced glycation end products, or AGE. Over weeks and months, the Amadori products will undergo a chaotic series of dehydrations, fragmentations, and oxidative reactions. And this final irreversible step yields a heterogeneous group of toxic compounds, the advanced glycation end products, or AGEs for short. And once these AGEs accumulate in tissues, they inflict structural and cellular damage through two primary pathways. First is extracellular cross-linking, and second is receptor-mediated signaling. There's actually a receptor for advanced glycation end products. So we get structural damage via macromolecular cross-linking. That's when the AGEs act as molecular glue, and they form covalent cross-links between adjacent protein fibers, particularly long-lived structural proteins such as collagen and elastin in the extracellular matrix. And of course, we can get vascular stiffening. That's when we have cross-linking in the arterial walls. That strips blood vessels of their elasticity. And this directly contributes to endothelial dysfunction, arterial stiffness, and hypertension, high blood pressure. Then we can get neuropathy. And so in the kidneys, glycation of the glomerular basement membrane alters its filtration permeability and this allows vital proteins to leak into the urine. That's called proteinuria, and that eventually leads to diabetic kidney disease. We can also get receptor-mediated damage, and that's when we get what's called RAGE, or the receptor for advanced glycation end products. And so cells express a specific surface receptor, appropriately named RAGE. And this RAGE protein, when circulating or tissue-bound advanced glycation end products bind to RAGE, it triggers a dangerous intracellular signaling cascade. And so we can get chronic inflammation. The advanced glycation end products and receptor interactions activates the pro-inflammatory transcription factor NF-kappa beta. And this turns on the expression of inflammatory cytokines, kind of like TNF-alpha or IL-6, interleukin-6, as well as adhesion molecules, and this keeps the vascular system in a state of constant low-grade inflammation. And we get oxidative stress. RAGE activation stimulates NADPH oxidase, unleashing a massive wave of reactive oxygen species. And this oxidative stress damages cellular membranes. It oxidizes low-density lipoprotein, or LDL cholesterol, and this accelerates plaque buildup, the condition known as atherosclerosis. And so doctors rely directly on the early stages of this in vivo Maillard reaction to monitor diabetes, because red blood cells live for about 120 days, and the protein hemoglobin inside them undergoes continuous glycation that's proportional to the amount of sugar in the blood. The resulting Amadori product is hemoglobin A1C, or HbA1c. And measuring a patient's HbA1c percentage provides clinicians with a highly accurate 3-month average of their blood glucose control, and that captures the real-time footprint of the body's internal kitchen chemistry. You generally want your A1C to be less than 5.7%. And when you go above about 5.7%, 5.6, 5.7, that gives you what's called pre-diabetes, and as your percentage rises even further, then like if it's above like 6.5%, that's diabetes right there. So this gives us a really good measure, and a little bit more accurate, a little bit better than just measuring your blood sugar at very specific intervals. We're actually looking at an average of your blood sugar over time. And so here's the structure of glycated or glycosylated hemoglobin. And we see I've colored in the 2 alpha and the 2 beta chains. And of course at the center of that we have our heme groups. We can kind of highlight those a little bit. There's 4 heme groups, and these are iron-containing porphyrin rings where oxygen is bound. And oh hey, look at that. We actually have an oxygen bound right here as well. So not only is this glycosylated hemoglobin, this is also oxygen-bound hemoglobin as well. And there's another oxygen there too. So there's the hemoglobin. Now let's look here, because we wanted to look at the glycosylated hemoglobin. So let's highlight this molecule right here. And I'm just going to blow this up and show the space-filling representation. That's a molecule, glucose, and it's right between 2 amino acid residues. So we have a threonine as well as an aspartic acid residue here, an aspartate. We can also see that this is non-covalently attached. But let's look a little bit inside here, and let's look at this molecule a little bit lower down here. Oh, look at this. This gets a little bit more interesting. That's a fructose molecule. And let me put this on so we can see the hemiketal ring binding form of the fructose. And this residue, the amino acid, this amino acid is a lysine. It's lysine 99. And so I guess the space-filling representation might not be the best to show the bond formation. So let's change that. And now we can see the bond that's formed by the glycosylated hemoglobin. And so that's the Maillard reaction in action. We can actually see a sugar molecule attached to the glucose. And that's the basis right there of the A1C test. So, how can science overcome this, identifying treatments for these diabetic complications? Scientists are looking to exploit this pathway by targeting with glycolysis inhibitors, such as 2-deoxyglucose, or lactate transporter blockers, MCT1, 4 inhibitors, as well as metabolic dietary shifts. Inhibitors such as aminoguanidine and pyridoxamine scavenge reactive dicarbonyls to prevent late-stage advanced glycation end product formation. There's also compounds under investigation like alagibrium, ALT-711, and these are designed to chemically sever the covalent bonds between cross-linked structural proteins. So the Maillard reaction is much more than a simple reaction to make food taste better. It's a complex biochemical reaction that bridges the gap between molecular gastronomy and chronic metabolic pathology. So I hope you enjoyed this exploration into this very important reaction. If you have any comments, leave them down in the comments section below. If you have any questions, leave them there as well too. I like to read these comments, and that kind of helps you see what you're thinking. Please go ahead and hit the little like button, and if you found this video helpful. Go ahead and subscribe to my channel. Hit the little bell icon so you're notified when I have new and interesting content. Once again, thank you for watching. And I appreciate all the views that we get from these videos. Thank you.